So we're beginning Unit 2 by looking at the properties of water, which is Chapter 3 in your textbook. But before we can really understand water's properties, we need to understand more about what is discussed in Chapter 2, which is the basics of chemistry. So chemical reactivity, it all comes down to an atom's tendency to completely fill its valence shell or to empty a partially filled valence shell. And this is the tendency or the property that drives chemical reactions. And most importantly for this discussion, what creates bonds. So as you will recall, hopefully from chemistry, we have weak and strong bonds. The strongest bonds are the covalent bonds, where the two atoms share their electrons equally. So, for example, with hydrogen gas, we have two hydrogen atoms that will share their two electrons equally there in a covalent bond. The weaker bonds include hydrogen bonds, which are in contrast to the hydrogen gas here. These hydrogen bonds are simply an attraction between a positive and negative charge. So as you will recall, the hydrogen has its one electron, and so that one electron will have an attraction to any negative charge or any positive charge. And so that is one of the characteristics that are important with water, and we'll look at that a little bit later. With hydrophobic and hydrophilic interactions, we again have this play between positive and negative attractions. And with van der Waals forces, we also have a weak bond, but something also that has to do with this interchange or interplay between positive and negative forces. And so between the positive in the protons versus the negative in the electrons of each atom that's interacting. And then finally we have our ionic bonds. So nonpolar covalent bonds, the definition of that is a pair of electrons that are shared equally by two atoms. For example, with hydrocarbons, which are a big part of most biomolecules, so carbon and hydrogen together, we have these hydrocarbons that will share their electrons equally. And so there's no polarity in those molecules. They're very stable. There's also lots of energy stored in this type of bond, so that when we have those bonds released, we get a very strong reaction. As you can see with methane there, it is extremely, it has a number, 4 of these nonpolar covalent bonds, and so when we have that ignited and pulled apart, we get flames. The next here too is when we have polar covalent bonds. So in this case, we have a pair of electrons that are being shared still, because it's still a covalent bond, but they're not shared equally. So one atom tends to be more greedy than the other. So the example again of water, we have the oxygen atom, which pulls away the electrons from the hydrogen atoms, so that it draws them out of its valence, but not completely, so that they're still shared, but at least they're pulled into the direction closer to the nucleus of the oxygen atom, where we have the protons and neutrons. So we end up with polarity in this type of molecule. So when we have, for example, water, as you I'm sure will remember, water is a polar molecule, which means it has a positive end and a negative end. And this is what leads to all of the emergent qualities or properties of water. So this is a very strong bond, again, because it is still covalent, but it makes the molecule much more interactive. For example, oxygen has that strong attraction for electrons, and so that negative end of the molecule can then be attracted to another molecule that has a more positive charge. Now, when we don't have that sharing of electrons, we actually have ionic bonds. And so in terms of ionic bonds, we have one atom stealing the electrons from another. So a bond is made because there's still now this attraction between a positive and a negative atom. But in this case, the electron has actually been taken or given away to the more electronegative atom. So electronegativity, as a definition, is the amount of force or draw that an atom has to attract electrons or steal electrons. So hydrogen bonding, primarily with water molecules, which are polar, we get an attraction to other molecules. And that attraction is based on the positive hydrogen end of the molecule being attracted to the negative oxygen in another water molecule. So this is again a weak bond, as we discussed earlier, but a very important and common one in biology. The other type of force that we discussed is van der Waals forces, and this is when we have the opposite charges in different regions of a molecule attracted to each other. So it's not an actual bond, it's really an attraction. And it has to do with the fact that, as if you'll remember from chemistry, the electrons are constantly moving. And so a molecule can go from having its electrons close to another molecule to having them far away. And that simple and very quick change in polarity, because as the negative charge moves away, the electron moves away from the other molecule, it takes its negative charge with it. So it makes the end of the molecule that's exposed to the other positive. And so this changing positive to negative polarity, that's a very subtle change, is what's responsible for van der Waals forces. And so it allows things like the gecko to be able to attach itself upside down to a ceiling. And the way that it does that, if you'll look at this picture here, it has these little ridges on its feet, which really, if you were even going more microscopic, you would see there are just hundreds, if not thousands, of these little ridges that are on the foot of a gecko. And those each provide surface area attachment to whatever the gecko is trying to attach to. And so what it's doing then is all of that surface area is experiencing or allowing the van der Waals forces to attach and detach as an attraction to the molecules in the ceiling. And so the molecules in the ceiling, are stable. They're not really experiencing this. And they're simply there. But these thousands of atoms and molecules in the foot of the gecko actually are going through this van der Waals experience, and they're allowing the gecko to actually use that attractive force to stick to the wall, to make a bond that's temporary to the wall. But since it's continually changing, they can also lift that foot away from the wall and place it, to take a step. So that's essentially how van der Waals forces work. So now with that basis, we'll look at the properties of water, where a lot of these forces play a big part. So we'll start with this animation of the structure of water, which I know will be a review, but it's a good review. So it's important. I hope you noted there that a very important part of hydrogen bonding and the emergent properties that water then has because of this bonding is really based foundationally in water's ability to, as a molecule, bond with 4 other water molecules. So check and see how that works out. So we end up with 2 water molecules with the attraction to the negative portion of another water molecule. And then we have the negative portions of these water molecules attracted to the 2 hydrogens, which are, of course, having a more positive polar charge. Let's see if there's something else. Let's see. I think that covers all of it. Yes. Okay. So moving on. So polar water molecules create these attractions between other molecules as well. And this is actually repeating a lot of the same things, so we're just going to move on. But you can see the other thing that's brought up in this slide is that hydrogen bonding is also what holds a DNA molecule and RNA molecules. But DNA in particular here with its backbone, that's the phosphodiester backbone there, is also held together with the bases in the middle. These 2 strands are held together with hydrogen bonds, which means that this is obviously not a water molecule in the middle. These are different molecules, but the important thing is that they have hydrogens within these bases that have that same attraction. So the 4 emergent properties of water contribute to how life actually can occur on Earth. And those 4 big properties are cohesion, adhesion, which is very similar, the ability to moderate temperature, the way water expands when frozen, and the ability to act as a solvent. So its versatility as a solvent. So those are considered the 4 big emergent properties of water that actually sustain life on Earth. So we'll look at each one. So the first one being cohesion. That's when we have the hydrogen bonding between the water molecules that makes water sticky. So this is what's responsible for the surface tension of water, or as you can see in that picture, water droplets actually forming and sticking together. The water molecules stick together to make that bubble that is a water droplet. It's also responsible for the capillary action, which draws water up a small tube, the ability to use a drinking straw. And also cohesion, it plays a part in the transport of water in plants. So we'll look at that a little bit more. But essentially what we end up having, again, thinking back to that picture where you have a water molecule and then it has 4 hydrogen bonds to 4 other water molecules, allows water to make like a matrix, like a lacing together layer that provides a pretty sturdy surface tension. So enough of a matrix is made that you can have this action here of this lizard that can